Mm-hmm. Yeah, the funny ones. Well, if you really want to hear me like be mad, you should watch one of the Math and Society videos because it's me being like, "Why is your foot on the desk? Put your foot down. Put your foot down. Put your foot." Like it's just like that. Okay, so let's say that we're standing on the top of a 100-foot building. So that's you, and we're gonna drop a tomato. This is the tomato.
Or not?
I don't know. You can have it be a rock if you want it to be. It'll fall at the same speed.
A penny?
Right. The tomato partly because it splats at the bottom. Okay, so what I did is I really quickly charted out the height of the tomato at different times. So at time 0, when we're at the top of the building, it's at 100 feet. After half a second has gone by, the tomato's at 96 feet. After 1 second has gone by, it's at 84 feet. 1.5 seconds, it's at 64. 2 seconds, it's at 36 feet. And then 2.5 seconds, splat, it's on the ground. So there's a few things that we can calculate really, really easily here just from the table. So first of all, how far was the total distance the tomato fell? Great. How far did the tomato fall in the last second?
The last second?
Mm-hmm.
64 feet.
Okay. How far did the tomato fall in the first second?
Or 16.
Yes, 16. 100 minus 84. Okay. Okay, now we can also find out what the average velocity is. Now, velocity and speed are similar to each other, but they aren't the same. The difference between velocity and speed is velocity has a direction, whereas speed does not. So if you're traveling in your car and you're going towards the school, your speedometer is going to read, I don't know, 70 miles per hour, 25 miles per hour, wherever you're traveling from, right? And if you're traveling away from the school, it won't register that as the opposite. So if you're going towards the school and away from the school, it registers the same speed. Velocity is different. Velocity has a direction attached to it. If we're talking about your velocity in relation to the school, it would be positive if you're coming towards the school and negative if you're going away from the school. Does that make any sense?
Yeah, we're doing this in physics.
Okay. So here, if I want to talk about average velocity, if I'm looking at the entire thing, I would just find out the displacement in feet. So the final feet minus the first feet, so 0 minus 100, divided by how much time it took. So the average velocity would be 0 minus 100 divided by 2.5, and it's not 40. 40 would be the speed.
Oh, wait, never mind.
It's negative 40, and that's feet per second. The reason it's negative is because we're talking about velocity, and we have a direction. It's going down. Kind of, sort of? Now, there's a few things that are a little, all of those questions I just asked are really easy to answer just from the table. There are some questions that are trickier to answer from the table. For example, if I wanted to know the speed it was going at exactly 1 second after it dropped. So I want to know the exact speed it was 1 second after it dropped. That's a little trickier. I could take the displacement from 0 seconds to 1 second, which is 16 feet, and divide that by the time that it took. So I could say it was going negative 16 feet per second. But as you can see, as the tomato falls, it speeds up. So is this the average velocity from 0 to 1 second? Is that going to be the same as the instantaneous velocity at 1 second? Okay, and the reason why is as it falls, it speeds up. So every moment it's falling, it's gaining more velocity. Do you guys see that?
Yeah.
So there's a difference between average velocity and instantaneous velocity. So what we can do to try to find this instantaneous velocity for now, we're going to learn how to find it exactly in this chapter. But for now, what we can do is we can find the velocity from right before 1 second to right after 1 second, find the displacement between those two, and then divide by the time between those two. What? Oh. So needy. Okay. So from 96, or from 0.5 seconds to 1.5 seconds, what's the displacement between those two? 1 second is the second part, and 32 is the feet. So it's going from 64 minus 96 divided by 1. So the velocity isn't going to be 32 feet per second, it's negative 32 feet per second. And this is just an average. This is our best guess at this point in time about the velocity at the moment it's 1 second after it fell. I can do the same thing to try to find out what the velocity at 2 seconds is. can find the displacement between these two. So 0 minus 64 divided by 1, and I get negative 64 feet per second. So the average velocity for the entire trip is about 40 feet per second, but you can see between our estimates at the velocity at 1 second and the velocity at 2 seconds that it's speeding up the more it falls. And I mean, you guys have fallen before or watched things fall. That seems to make sense. Things speed up the longer they go. It would be weird if things didn't speed up, like if you dropped something and it kept a constant velocity.
That'd be cool though.
It'd be really weird. It would look like things were floating, but as things drop, they speed up. Kind of, sort of? All right, so what we're talking about today is the difference between a secant line and a tangent line. So here we go. So a secant line.
What should we title these notes?
So we'll title the notes Tangents and Secants. All right, so I want to say this right. I'm going to say it wrong if I just say it from my memory. So I'm going to actually use your textbook here. Okay, so the secant line is the, in this case it's average. In this case it's velocity, but it won't always be velocity. Sometimes it'll be other thing. Average velocity between 2 points is the slope of the secant line. Secant line. And you guys have heard that term secant before, back in pre-calc. We're not going to use it the way that you used it in pre-calc for a little bit. Okay, so a secant line is what we were doing here. So like this negative 32, this is the slope of a line secant to the graph of this from 0.5 to 1.5. Now, the smaller you make that difference, so like instead of having my table at half-second intervals, if I had it at 1/10 of a second intervals, then I would go 2 points that are even closer to 1 second. And I could go even like hundredths of a second and go even closer, thousandths of a second, go even closer. The closer and closer and closer you get, you approach having no distance between the point that you're looking for and the point that you're using to make the secant line. That is how you get close to an instantaneous velocity. Does that make any sense, what I just said? Okay.
Can you ever get an instantaneous
Yes.
velocity?
Using calculus. So the difference between a secant line and a tangent line. So a tangent line isn't the average, it's what's called the instantaneous velocity. It's the instantaneous velocity. And instead of being between 2 points, it's at a point. And that's the slope of a tangent line. Now, you guys last chapter had to do some, like, essentially just guessing about slopes of tangent lines. Today we're going to get into nitty-gritty math and actually find it. Tangent line. Okay, so essentially what happens is you can use a secant line here because you have this interval that you have to use. The smaller these intervals become, the closer these intervals approach 0, the closer you become to not finding the slope of a secant line, but the slope of a tangent line. And so those two things are different. If you're looking at like a graph here, I'll show you what the difference of the two of them is if you're looking at a graph. So let's say we have y equals x squared. And I'm just going to just sketch this. So y equals x squared looks something like this. If I choose a point here, let's say that this point is 2, 4. If I wanted to find a tangent line, it would be the slope of a line tangent at that point. I could, however, do a secant line by taking 1, 1 and 3, 9 and finding the slope in between those two. And that would be a rough approximation of the tangent line slope. Kinda, sorta. Let's get into the nitty-gritty math so that you guys can actually see what's going on. So, let's say that we have an equation here, and I'm going to start out really simple. Let's say that we have a function f of x is equal to, let's do x squared plus 1. I know for a fact this function goes through the point 2, 5. Because if I plug 2 in for x, I get 5 back out for y, right? Now, I haven't taught you how to find the slope of a line tangent yet, and so we're kind of fumbling at it the way that Newton fumbled at it before calculus was discovered, Newton and Leibniz, before calculus was discovered. So if I want to find the slope of a line tangent here, what I can do is I can, say, take the point 2.001, plug this into the function, and find out what I get back out for y. So that's what I'm going to do first, is plug in 2.001, a point that is very, very close to 2 on that line. I'm going to plug it into the function using my calculator, because Lord knows you don't want to do any math this early in the morning. So we'll do 2.001 quantity squared plus 1, and I get back out 5.004001. So I'm going to be super exact this time. I'm going to keep all those decimals. 004001. Now, if I want to find the slope of the line tangent, I just find the slope between these 2 points. We're going to have decimals inside decimals, so don't freak out about that. If I subtract top minus bottom, I'm going to get 0.004001. That's the difference in y. And then the difference in x is point. Right. And now I'm going to use my calculator to actually find out what that is. Divided by 0.001, and I get back out. This is my first rough approximation of the line tangent to this graph at this point. I'm sorry, say that again? And got the 0.004001. 2.001 minus 2 to get 0.001, and then I just divided these in my calculator, and it spat back out 4.001. So this is my rough approximation of the slope of the line tangent to this equation at this point. Now, the slope of the line tangent is going to change depending on which point you look at. The slope of a line tangent here is going to be different than here, is going to be different than here, is going to be different than down here. Right? You guys remember drawing that out? Kind of, sort of? I had a question on your test, and honestly, there were 3 answers I accepted. On the test, you had a graph that was like this, and I asked for the slope of the line tangent right there. If you said 0, I accepted it, because you could make an argument that 0 is the line tangent. If you said 1, I accepted it, because that's what it was over here. But if you were doing a secant line, it really should be 0.5. But I accepted all 3 of those answers. I think everybody answered 0, 1, or 0.5. 0.5 is the best of them, but no matter. You all got points for it. Okay, so this is part of what's going to be on your assignment today, is you'll be given an equation and a point that's on that function, and then you're asked to find the slope of a line that goes in between this point and some other point that's really close to it. So like it could be 2.001 or it could be 1.97. That's why I had you guys do what I had to do for the warm-up. Now the other thing that you'll have to do is, let's say that we have this same function here, and I want you to find, so our function is f of x equals x squared plus 1, and I know that this goes through the point 2, 5. I want to find the slope between, or not the slope, the equation of a line tangent here, and then the other point is going to be 2 plus h. So now I have to evaluate this function at 2 plus h. So that means I need to do parentheses 2 plus h quantity squared plus 1. So 2 plus h quantity squared is not 4 plus h squared. It's 4.
4 plus 4 h plus h squared.
Nice, you guys are getting better at doing that quickly. Plus 1. I know! 4h plus h squared. It's almost like I planned this or something. Plus 1. All right, so now if you subtract these two, the 4 and the 5, or the 4 and the 1 make 5, and they, like if you're doing this minus that, they're just going to cancel with the 5. So for your difference in y, you've got 4h plus h squared. If you subtract your x's, 2 plus h minus 2 is just h. well, hey, this looks like stuff that I was trying to prep you for last chapter, right? So you end up with 4 plus h. Now, what's the slope of the line tangent as this h approaches 0? What does the value approach?
4.
Mm-hmm. So if I put in like a super, super tiny number here, like 0.000000001, 4 plus that number is going to be pretty darn close to 4. So the slope of the line tangent at this point is really just 4. Kind of, sort of. This is the groundwork of calculus. We're going to learn something next chapter that you guys are going to hate me for making you do all this work for. But that's how all math is. This is the groundwork of it. It's hard to understand what comes after if you don't understand what came before. So let's take a look at our assignment today. Yeah, that's all your notes. I don't think today's stuff is super difficult compared to some of the stuff from last chapter. I could be wrong though. Your mileage may vary. So your assignment today is 1 through, I want you to do 1 through 8 or 1 through 9?
1 through 8.
No, I'm aware what you want. What I want is the question.
You want 1 through 8.
No, 1 through 9.
1 through 2.
I mean, you can do that. So let's take a look at question number 1 here, just to get you guys started. Question number 1 is super similar to what we were just doing. We've got what's the slope of the line through 3, 9 and xy for y equals x squared and x equals 2.97. So let's do that one first. So we know that it goes through the point 3, 9. And now we're going to evaluate this function for x equals 2.97, a value that's really close to 3. So go ahead and use your second brain and have it tell you what 2.97 squared is.
8.8209.
Cool. I'm going to keep all of those decimals. Now if I subtract these two, this time I'm going to do top minus bottom. So I'll do 9 minus whatever that was. 0.1791. And if I do 3 minus that, it's 0.03. And if I divide those two, I get 5.97. So that's the first answer to question number 1. For 1, 2, 3, I think it's 4, you don't have to sketch the graph. It says sketch the graph. You don't have to do that. You just have to do the values of x and then where x is 3 plus h. And then enter what happens when h is very small. So if we do this again, so the point is 3, 9, and we're doing 3.001, substituting that in for x. 0.001 squared is 9.006001. If I subtract those two now, I'll get, am I going too fast here? And then, so you get 6.001. And now you have to do it for 3 plus h. So
Is that a
I did this minus that. You can switch the order depending on which is easiest for you. They're like that. So like on this one I did top minus bottom, on this one I did bottom minus top. You can, so long as you're consistent, so long as I'm not doing bottom minus top and then top minus bottom in the same problem, it doesn't matter. Okay, and then for 3 plus h, probably, there we go. Okay, for 3 plus h, you know that it goes through the point 3, 9. And then 3 plus h is your x value, and then your y value then is going to be 9, 6h plus h squared. And then if you subtract these, 3's cancel, leaving you with an h on the bottom. 9's cancel, leaving you 6h plus h squared on top. And then if you divide everything by h, you've got 6 plus h. And And then the last question here for number 1, what happens to this last slope when h is very small, close to 0? What value does it approach? Yep. And then you don't have to sketch the graph. Okay. So question number 2 is the same function, y equals x squared, but for a different value. You're using the point -2, 4, and then you're going to substitute -1.98 in for x, find the y value, find the slope between those 2 points. -2.03 in for x, find the y value, find the slope between those 2 points. -2 plus h in for x, find the y value, slope between those 2 points. And then what happens to the slope when h is very small, close to 0? You don't have to sketch the graph. Okay? Kind of sorta? Alright. So